Hello everybody, my name is Alondra Pereira and today I'm going to show you my implementation for the shortest path routing problem. The shortest path problem is a core problem in computer science that is present in everyday tasks. Some of its applications are computer networks, transportation planning, social network analysis, and many others. Right now there are several options meant to solve this, and these options are Dijkstra, Floyd-Warshall, Bellman-Ford, and A-star algorithm. Dijkstra algorithm was proposed in 1956 to find the shortest path between nodes in a weighted graph. The Dijkstra algorithm operates based on the greedy principle, which implies that it makes the best possible decision at each stage, leading to an optimal global solution in the end. And now I'm gonna show you the pseudocode for the implementation that I made. Okay, so here we have the pseudocode for Dijkstra shortest path. We have three different inputs: the graph start node and end node. We are going to initialize several variables, and then we're gonna do a loop while we have elements in our cube. After that, we're gonna pop the cube, and we're gonna obtain the current distance, current node. After that, we're gonna initialize a list, and then we're gonna check if our node is the end node. If it is, then we're gonna add this current node to our path, and then we're gonna change the current node to the previous current node. And after that, we're going to reverse the list because it's gonna give us the inverse order. And finally, we're gonna return the path and the distances because we want to know why it was chosen the shortest path. But that is only if we find the end node. If we don't, we're gonna go to this part of the code. We're gonna add the current node to the visited list, and we're gonna look. We're gonna have the neighbors, the weight in our graph current node. After that, we're gonna check if this neighbor is not in the visited, that is to say that hasn't been visited, and we're gonna check if the current distance plus weight is less than the distance that we currently have. If it is, then we're gonna swap distances and the temp distance because it's smaller and it's leading us to the shortest path. Okay, so now I'm going to show you my implementation for this problem. It's pretty similar to the pseudocode that I just explained. We have three different variables. We start initializing the different things that we have. We have the same loop. We DQ the current distance, current node. Then we check if our current node is the goal node. Then we have another list to save the path, and we're gonna append current nodes until we have nodes. After that, we're going to reverse the list because it's gonna give us the inverse order. So after that, we just return the path and the shortest distance. That is if we reach the end node Otherwise, we're gonna basically set the node as visited and update the distances to its visited neighbors. And this is what we're doing here. Right here, if we find a distance that is shorter than the one that is currently being saved, then we're gonna swap. Yeah. So if we get to the end of the code, that means that there is no path between the start node and end node. And here we have the example network that was given in the instructions. And here we are testing this algorithm with 3 different paths. I think we're ready to run everything, so we're gonna do it right now. And here we have our 3 different results. I hope you enjoyed this video,